That's evolution. It just works that way. Yes, sir. It has to happen at the same pace of RNA polymerase II elongation. RNA polymerase II makes about 40 nucleotides per second, and thus as every intron emerges from RNA polymerase, it needs to be immediately recognized, the branch point found, and the intron cleaved. Now realize certain introns are 10,000 bases long, so it's going to take RNA polymerase 500 seconds to do that. So a splicing reaction might take somewhere on the order of 10 minutes. The chemistry itself is ridiculously fast, but it matters getting all the pieces of the puzzle there in order for things to happen. On very small introns, of course, it has to happen exceedingly rapidly. You might be cleaving an intron every 2 seconds. There's one more question about this.
No, I'm good.
You're good? All right, even better. And please, interrupt. I don't know if Eric allows you to interrupt, but I do. Yes, sir?
What is U4 and U6?
Well, I'm going to show you on the next slide in very details. So here's some of the rearrangements that occur. Again, I told you that U1 was initially responsible for recognizing the exon intron boundary at the upstream edge. U6 comes in to replace U1 and take over. So U6 is primarily responsible for recognizing the 5' splice site junction after it's been recognized by U1. Here's another exchange, and I'll get to U4 and everybody else in a second. The branch point binding protein again gives way to U2, and you can sort of see these SNRPs. They contain RNAs in them, and those RNAs, through direct base pairing, allow things to find the proper splice site junctions. Again, if you put things back together incorrectly, you just end up with garblio. It's not going to help anybody. So we're not going to force you to learn much more about U4 or U5, other than to say that I can explicitly tell you that U5 is responsible for pairing with both the upstream and the downstream exon to allow the transesterification reaction to go through. U4 is largely a molecular placeholder. It actually helps push the lariat out of the way, but it's beyond the technologies and informations that you're going to need to do great on your exam. I mean, Phil Sharp can tell you what they all do in crazy, crazy detail. But you can imagine that, how long it took to work this out. They all had to be purified. They all do overlapping things. They bind to the same site. You have to add them in the right order. And so there is a large number of additional proteins that are simply responsible for getting these things on and off the RNA in a logical manner such that it can happen. So we got about 5 minutes. I'm going to review just a few things here. So, again, yes, ma'am?
So does U2 vary based on what cell type it's in? Because it has to bind to different sections of exons. I'm just curious, does the structure then change?
No, the structure doesn't change, nor does the composition of the particle. There are, again, these accessory factors that help orchestrate the loading and unloading of all of these. And in different variants, I'll just skip ahead here for a second. So here's some more about what U4 and U6 and U5 do and how they pull everything together. But in different, probably the easiest one here is muscle. So in different cell types, there are accessory factors that are produced that either block or accentuate the use of certain splice sites. So your striated muscle, for instance, puts together the exons that are in the top line. But your smooth muscle puts together a completely different set of axons, not a completely different set of axons to generate things. And this is where the tissue-specific factors come in. These splicing SNRPs don't change. They need that basic chemistry and that basic functionality to them. But specific factors can direct them to or block their activity at certain sites so that you can end up with different splicing variants. Yes?
Do all the SNRPs make up the spliceosome?
The entirety of the SNRPs make up the spliceosome. It's difficult to define a spliceosome because its composition is constantly in flux. So U1 is part of the spliceosome, but it gets kicked out at a certain point. So it's sort of an amorphous thing, what the spliceosome is. But the entirety of those SNRPs, together with the RNA, together with the accessory factors, are responsible for generating the splicing reaction.
So once the lariat is formed, how does the
itself off the RNA. So when, I'm not tall enough, but when this blue exon attacks the blue exon on the other side, it's making a new bond between blue and blue, and it has to give up the bond between blue and yellow.
Okay.
And so when the blue and yellow bond is severed, that's the second transesterification reaction. We're switching one DNA bond for the other.
Okay.
The blue one was single and alone. Now the yellow one's going to be single and alone, and it will soon be degraded and die.
Okay.
I guess we're going to have to stop there for today. We'll pick up the topic next time.